So here we go. You can figure out the DC value, or rather the initial condition of the capacitor, as follows. So we are saying that the capacitor voltage is given by, the input voltage is given by I, and I is up here for a long period of time. Let me get red. This is the axis that I'm showing here. Switch back to green. So since the input voltage is at I for a long period of time, in the circuit here, since I have a DC value I for a long period of time, the capacitor will have settled down to its final value. Okay, so all the dynamics of the system will have played out. Okay, for this first order circuit, where I usually see falling exponents, or I see rising waveforms of the form 1 minus e raised to minus t over RC. The dynamics of these storage elements like capacitors or inductors will all have settled out. Okay, so after a long period of time, the capacitor will look like an open circuit. So if the input current was I, and if the dynamics of the capacitor have settled out, in other words, it's not going to be, I'm not going to be charging it up any further, and it looks like an open circuit, then this current I must be flowing all the way through R, and so this node here will be at voltage IR. Okay, so after a long period of time, from minus infinity all the way to t equals 0 minus, if the value of the input is at I, then the capacitor voltage will be at IR. Okay, because the capacitor voltage is at IR, and the I current flows all the way through the resistor in the steady state. It is not going to flow through the capacitor because that looks like a open. So it's going to all flow through the resistor, providing a voltage IR. So the voltage across the resistor IR equals the voltage across the capacitor, which is also IR. So VC 0 minus is equal to IR. So I'm hoping you can practice various examples from the book and your homework and exercises, and just intuitively figure out what the value of capacitor or inductor voltages will be after long periods of time. Okay, in this case it is IR. Okay, so the VC 0 minus is IR. So at time t equal to 0, I now have the value of the capacitor voltage, and that is given by IR. All right. So then at time t equal to 0, my input takes a nosedive. Okay, my input dives to 0. Okay, my input goes down to 0. So what happens? So my input goes to 0. My capacitor has an initial voltage IR across it. And so therefore, this capacitor with voltage IR across it will now discharge through the resistor, because notice when this current source has 0 current, this is going to look like an open circuit. Okay, where current source is not supplying any current, it will look like an open circuit, and so the capacitor with its initial condition IR will begin to decay, will begin to discharge completely through R. All right, so in this situation, notice that what I'm looking for is the 0 input response of this little first order circuit. Okay, it's 0 input response because the current is 0 and the capacitor has some initial condition on it, and so it's the ZIR. After a long period of time, the capacitor will completely discharge, and the voltage across the capacitor will be 0. So in this case, not surprisingly, I'm looking for a form that looks like this. Okay, so this form will be of the expression for this kind of a form is the decaying exponential. So here I'm going to get this decaying exponential form, and it will be of the form e to the minus t over RC. The initial value is IR, so I stick IR in here, and there you have it. Okay, so intuitively, I've very quickly derived for you what is the dynamics of the capacitor voltage. And just to be completely clear, notice that you can plot the value across the capacitor, the voltage across the capacitor like this. Okay, because it is going to be at IR for a long period of time before 0. And then at 0, the step is going to hit, the negative step is going to hit, it's going to go from I to 0. And that will cause the capacitor to start decaying all the way down to 0. Okay, so this is a falling step response of the RC circuit. Now, in case you're wondering why I'm talking about falling and rising step responses of RC circuits, you will find that out soon enough. Okay, just think about in your own minds a rising step followed by a falling step. That will lead me to develop the response for a pulse. Okay, and then if you're wondering why I'm doing the pulse, think about narrowing the pulse more and more. If this is a pulse, think about narrowing the pulse more and more, and that will give me an impulse. Okay, so we have done the rising step, we have done the falling step, and my next thing will be a pulse, which looks like this. Okay, pulse will be formed of a rising step followed by a falling step. Okay, and I'm just going to compose the two results you've seen so far and very quickly get the response for a pulse. Then I'm going to squeeze the pulse. Okay, I'm going to squeeze it, and that will give me an impulse. Okay, so I'm just going to do all of this by intuition, and I want you to follow along. It is very, very simple.